students here, and this is in fact maybe I went a bit too fast, but they pointed out, and it's correct, that actually the formation entropy of ethane is not in our tables. So then we could ask ourselves, how can we determine this X, and it is shown here. Actually, this is making all of the bonds between carbon and hydrogen in a molecule of ethane. And a molecule of ethane looks like this. Two carbons connected together, and then 6 hydrogens. So that means we now make in total 7 bonds. 6 times CH, 6, and 1 is carbon-carbon. These energies will be released when we combine the 2 carbons and the 6 hydrogens in the atom state. Now, how can we know these bond energies? They're actually also in tables, but we have to look at a different table, namely table 3. So let's look at table 3. It's over here. So these are the average bond energies and bond lengths, but we need the energies. So what we need is the carbon-hydrogen, here, 413, so there's 6 of them. And we will also need carbon-carbon, 1. That's 347 kilojoule per mole. So if we add it up, we get, in fact, X. So I will show it back again. Because that's what you do. You start from the atoms and you make all the bonds. In that case, you release the bond energies of all of the bonds involved. And so you can determine X in that way. In other ways, you would need delta HF of ethane, but actually we don't have that. So you could actually say that delta HF of ethane we could determine by closing our S circle, but then in an alternative way. There was another small remark, maybe I will also very briefly mention it. This is just my carelessness, but actually, as you can see here, this number has 4 significant numbers. This has also 4 significant numbers. So you could ask yourself, why only 3? And if you calculate it, it's like 981.5 or something like that. So you could as well probably give it 982. The answer is, it's just because I'm careless. And, but my reply to that is also, I'm careless because I actually don't care. And this is not the point. The point behind it is the theory, and that you understand, and how you get to this particular temperature. And that's by matching the enthalpy and the entropy, by making the ratio of the two. That's what you have to know. And if it's 981 or 982, nobody really cares. And I hope that if the teaching assistants correct your exam, that they will agree that this is the same. So that is not the point, I would say. Okay, let's move to chapter 12, which is our 3rd chapter on kinetics. I'm already going a little bit over time with my period, so I will make them a bit shorter now. Otherwise, the next speaker is going to be angry if I go over the time. I don't want to do that. So aspects of the chemical reaction, but we are no longer looking at the energies, but we are looking at the speed of the reaction, or as it is said in English, the rate of the reaction, well, making theoretical considerations from that. Now, the rate of the reaction could be considered in two different ways, because you always have reagents and you have products. So you could say the rate is the degree to which the reagents are disappearing, or the degree with which the products are being formed. So the rate is given by the letter V. I think it comes from the Latin velociter, so we hear velocity, which is a very expensive word for rate, for speed. So indeed, if you look from the reaction products, it's a positive number because it's increasing as the reaction is going. If you look from the reagent, of course, they are decreasing. So this is a negative. So, and you can see it as a function of the time. So this could be also seen, in fact, as a kind of differential of reagents or products in time. If you look at it, well, the concentration is in mole per liter, and time could be in seconds, or in minutes, or in hours, or in days, centuries. But I think the ESI normally is seconds, but of course, if it's a very slow reaction, you might want to use hours or something like that. So we're going to look at a few simple reactions, which will come back from time to time. And this is one where dinitrogen pentaoxide is being decomposed into NO2 and that oxygen. You can see the stoichiometry is 2, 4, 1. Okay, so we can now look at the rates, and actually this could be said it's the formation of oxygen. So in the time. It could be said it's a formation of NO2 in time, but there's 4 NO2s for every oxygen. So to make them equal, we have to divide by 4. Because the speeds at which the reaction is going will be 4 times faster for NO2 otherwise. And then, since we start with 2 equivalents of N2O5, the disappearance of that is going to go to at the half rate of the appearance of oxygen. But we have to change in sign, because we have appearance versus disappearance. Now, we could again make an equation, and then we have now a function of t, but it's small t, time, not temperature. So, and in function of time, we will see a straight line, and the slope will describe the change in concentration of the reaction product. So we come to the rate equation in a moment. So this is a typical way how this could go. So the blue line is the one that follows the concentration of the N2O5. It's going down, as you can see, but it's going down slower and slower, and it's actually never reaching 0, or at the 0 will be reached after a long, long, long time. This is like a hyperbole. Another thing that's in the kinetics is sometimes important is what is the half-life. And the half-life is the time that you need to go to the half of the original compound. So in this case, we start from about 0.016. So when we reach here, which is the half, we are here on the graph, and if you go down, that's the time, and that's the half time. That's it says something about the reaction. So when is the half time? Sometimes the half time is constant, sometimes not, and we will see in which case that is. What you also see is that the slope, so this is the slope in the beginning of the reaction, but the slope will every time become more flat as we continue. In the beginning it's at its maximum value. So very often people consider the initial speeds, the initial rate of the reaction, and that's then this red line that you see over there, and they make some theory from that. So that's the so-called initial rate. The rate goes down because you have less and less reagent. That actually means it's in function of how much reagent is left. So let's look here at these initial speeds of reaction and see if we can deduct something from it. So this is a reaction, it's an oxidation of iodides with hydrogen peroxide. And you form, in acidic medium, you form triiodide and you form water. So, and water is a solvent, so we don't really need to consider it as a product. I think what we could look at, if we consider the three reagents, hydrogen peroxide, acids, and iodide, what is the effect on the rates, on the initial rate? Well, we can, in this table, actually compare. These are the concentrations of these reagents. You can see actually the protons, the acid, is catalytic. It's not in the same ratio as you have for the iodides and hydrogen peroxide. Now, if you look at line number 2, everything is the same, except for the concentration of hydrogen peroxide that has doubled. Now, if you look at the initial speeds, you see also the speed is doubling. It's the unit in mole per liter per second. Okay, what's about this line? You can see now, between the first line and the third line, the difference is again that we double, but we double now the iodide concentration. And you can see again, we get the doubling of the speeds if we compare line 1 with line 3. Now with line 4, everything is the same except for the proton concentration, for the acidity, which has doubled. And now what we see is no effect. Okay. Line 1 and line 4 is the same rate. Doubling the acid doesn't really make any difference. Now, this means if we now make some kind of relation of the speed to the initial concentration, so we can say that it's directly proportional to the hydrogen peroxide concentration. It's also directly proportional to the iodide concentration. So actually, this is the power 1, but power 1 is actually can be omitted. So that doesn't mean anything. mathematically, and in the power 0 for the H plus concentration. This actually means it's independent of the H plus concentration, because anything you put to the power 0 means 1. So this term goes away. So from this rate equation we can see that we have a rate which is dependent on only hydrogen peroxide and the iodides. So now, what can we conclude from this? Well, you cannot always know which kind of reagents are going to be important for the rates. Here, okay, apparently acid is not important, even though we see acid in our reaction equation. If you want to know what is actually going to be important, we actually need to know what is going on during that reaction. Because this reaction is actually only a global reaction. And there may be many intermediate steps. And these intermediate steps actually might be much more complicated than we know, and we actually have no information about it. We actually can get a little bit of information by doing this kinetic study. So we actually know that from this that acid is not important in the step that is actually the slowest of the whole process. Because otherwise it would show up in the reaction equation. By the way, we introduced K. So the changeable things are the concentrations. K is a constant. Small k refers to the rate. We will later also talk about big K, capital K, that is an equilibrium constant. But that's something for the next chapter. So, but it's very important to see the difference between the two. So the rate constant is a constant and therefore independent of any of the concentrations of the reagents or the products. So what is important, that the temperature is going to have an influence on the rate constant. So, and in fact, in most of the reactions, when you heat them, they go faster. The concentrations remain the same. You heat them, they go faster, that means your K is actually going to change. So it's a constant as long as the temperature is constant. Otherwise, it's going to be changing. What also is important in the equation that we just saw is, well, we have here exponents 1, 1, 0. And these exponents are called the order. And you can say the order of hydrogen peroxide in this reaction is 1. The order of iodides in this reaction is 1. The order of protons in this reaction is 0. And so people in many cases talk about the total order. Then it's 1 plus 1, 2. And this is a so-called second order reaction. And in fact, in the second order reaction, normally two particles are coming together in what is determining the rate. I will tell you more details about that later. So the order tells you something about the reaction mechanism, what is happening inside of the reaction. Okay, so indeed, global order is 2, or this is the second order reaction. So let's now treat the two most common examples. And the first order reaction is 1, and the second order reaction is the other one. Also, exist third order and so on, but we will not take, in this course, we will not discuss such complicated. Now, first order reaction is actually very simple. There's only one reagent that is of importance. And for instance, in the decomposition of dinitrogen pentoxides, we actually have a reaction that is first order in dinitrogen pentoxide. Even though maybe you could think two particles of this nitrogen pentoxide can come together, but no, apparently not. That's not the mechanism. So there's a first order rate constant, K, in this case. Very simple reaction. Sometimes reactions can be so-called first order. What does it mean? Means, in fact, it should be second order, but one of the reagents is present in so much excess that reacting with it doesn't make a difference, because the concentration is more or less the same before and after. Typically, if you do, for instance, your reaction in water, and there's a reaction with water, the concentration of water in water is going to stay the same. So, in that case, there's not going to be really some problem. So, to give the example that we just studied, so if you would have a very, very large excess of iodide in our reaction with hydrogen peroxide, then the reaction before and after the reaction would be the same. That means we now could treat this concentration as constant, and we just put it inside of the second order constant, the second order rate constant, which now becomes a pseudo first order rate constant. Yeah, a pseudo first order, because you see only one concentration term anymore. But for that we need a large excess, or we need that one of the reagents is a solvent. In that case, it would also go according to pseudo first order reactions. Now, we're going to do a little bit of very simple mathematics. So let's assume that the initial concentration of a reagent that is going to disappear is A. That's the number that we have. Then the reaction is going to evolve in time, and we will have a number for the concentration which is different from A. It's going to be A, and there's going to be something which is subtracted from it. We don't know exactly. It's a function, so let's put it X. So the concentration is lower than A, it is A minus X. So that's left of the initial concentration at any moment in time. So then the rate at that moment will be according to the concentration at that moment. Not according to the initial concentration, but the concentration at that moment. So at any moment, the rate is the rate constant multiplied by the concentration A minus X. And this rate also is the differential of A minus X over time. Now we can bring all the terms together. For A minus X, and then we put also minus K delta P. And now we integrate. Maybe you remember integration integration from your mathematics class in secondary school? This is a simple integration. If you don't remember it, just assume it. So that means it becomes a logarithm, a natural logarithm. And it means now you get the new function after integration, the logarithm of the concentration at any moment of A minus X concentration is added A, that's the logarithm of our initial value, minus K T. T time, and time is always a positive number, K is always a positive number, so that means this is a graph that is going down. Yeah. Because the slope is minus K. In the x-axis you have a T. So a descending line, but a straight line. And this is actually the way how you can know that a reaction is going to be first order. Plots the logarithms of the concentrations at any moment to the time. If all of the points are on a straight line, it's first order. We are sure. If you look at this graph of some time ago, this one here, this is the graph of the concentration, A minus X, in function of the time. Here, it's impossible to know what is the order of that. If we would make the logarithm of this concentration, and we know that it's the first order for this one, we will see it's a straight line. And then we have all the information that we need. So that's one way to find out about order of the reaction. Linear relationship is needed. So indeed, this is the graph that is very much looks like the graph of this N250, N205, sorry. So not really clear if it's first or second order. Here we have the logarithm. You see it cuts at 0 at the A concentration. In this case it's a big A, it's a capital A, but I think you get the point, it's the same. And this is at, there's a 0 because it's at the time 0, at the beginning of the situation. It's a slope that goes down. It is a rise. It's a straight line, so we know it must be first order. What about second order? So we can make a similar mathematical treatment. And again, I won't go into the details of the mathematics, you can just assume it. So there's an example also here where NO2 now, nitrogen dioxide, is being converted into NO and O2. And actually now, again, no way of knowing that. We just are actually finding this experimentally. We need the second order for NO2. So it looks like in the reaction mechanism, two molecules of NO2 have to come together. But that's why we have the second order in the concentration. So for such a reaction, we can now see that, okay, the concentration at any time is A minus X. We have again the differential of A minus X over the temperature. We bring all of the A minus X terms together, we integrate, and now the function is not a logarithm A minus X, but 1 over A minus X. So reciprocal concentration, you could say. As you can See also, as a consequence of the integration, the minus is dropped. So this is actually not a descending, but an ascending curve. Because plus kt is always a positive number. Straight line, ascending. So that means now we are plotting the data in a reciprocal way. We see if there's a straight line through it. If it is, we can conclude it's a second order reaction. So for instance, like that, you see ascending. We start at the points of 1 over 1 reciprocal. This is the lowest point, because A is the highest. Then 1 over A is the lowest. That's logical. And then from the slope we can derive the rate constants. Okay, I was promising that I would give smaller periods, so I'm going to give a break and then we continue. If you have any questions, you can always come in front.
giờ sao đâu. Bây giờ mình học tiếng Anh, đừng nói tiếng Việt, không biết gì được, không biết gì được. Inside the button. Nhưng mà cái này là cái resistance. Không resistance là cái nào? Resistance của battery.
Có định nghĩa chứ không?
Viết tiếng Anh đi được không? Có ấy mà. Có Wikipedia bằng tiếng Dương chưa bác? Cá tốt là công tâm nhỉ? Mình đang yêu phải là yêu âm hay là đang tổ ăn ớt bánh hoa. Calcium.
Không tôi sẽ biết người ta yêu theo
Mày lúc nào một đêm mà
Hôm nay trời cũng mát phết nhỉ, 24, 25 độ.
thì
Cái gì? Nó chỉ nhớ là thứ nhất là phải cho học ngôn ngữ từ một. Tôi là lý tưởng.
từ đây ra điểm, từ đây ra điểm, đến tận đây là tao có điểm. Từ đây sang đây tao chịu. Cái này là cái gì kết hợp? Cái này không phải ám. Mày có thấy là đây này. Đây đúng không? Thì reaction rate là define as an increase of concentration. Đấy, chính là tự nhiên đây là món đi phần về là món saturation, yeah. Cái mass nếu mà mày đang ở molar concentration thì có phải là decimal không? Thì ta bảo là chỉ có biết tốc độ của nó đây này, tính molar concentration. Thì thì có phải là phản ứng mất dần thì như sóng ở đây đâu. Bớt.
Okay, let's go back to the kinetics. So, we ended with this treatment of first and second order kinetics. I already mentioned to you some information about half-life, and now I think we can look at more details. What does it mean? Half-life for the first order and for second order reactions. So the definition of half-life, so this is the time that is needed for the concentration to reach its half of the original. So instead of A over 2. So in the first order reaction we can actually apply that to our equation that we found, which is a logarithmic equation. So then that means ln over 2, because that's a concentration at the half-life. That's ln minus k of the time at that moment. That's time and a half, half-life. So that means k time half is ln2. So actually k is a constant and ln2 is a constant. So we can conclude from that the half-life is also a constant. And now this is a second way to characterize the first order reactions. Because that's a characteristic, they have constant half-life, and actually we can derive from that half-life the rate constant. Because the half-life is actually ln2 divided by the rate constant. So for a second order reaction it's a little bit more complicated. And so in this case k 1.5 is 1 over a. So it's actually dependent on the initial concentration, and it's going to be non-constant because the concentration of course changes as we go. So the half-life in other words becomes longer and longer because the concentration becomes weaker and weaker. So you can derive this half-life from the graph, not of the logarithm, but of the concentration itself. So here we have plotted a minus x, the function of time, and we see this is like the same reaction that we saw before of N2O5. We start with the 1.6, a little bit more than that. The first half-life is at 0.8. It's over here, about 400 seconds, or yeah, in seconds. Now we see the second half-life is at 1/4 of the original concentration. That's about 0.4. That's, if you can see it cuts over here. We are at 800, 400, 800. You see, it's a constant. And if you go to 1200, that's a third half-life. That means we are at 1/8 of the original concentration. We divide by 2, by 2, by 2. 1/8. 0.2. So we can derive from this graph, without taking a logarithm, that this is a first order reaction. Because we see the half-life repeating. If it's going to be a second order reaction, this graph will go slower. So then it will not have this kind of profile, or if the order is in any way different. You see, to be accurate, you need a certain number of points. 2 or 3 data points are not going to tell you what it is. You need around, in this case I think we have around 8 or 7. I would say that's a really bare minimum to be able to do something. Otherwise you could draw a graph through, well, whatever you want. So you're going to need some points, and the points need to be evenly spread throughout the range of the time. So that means normally you would have to do experiments in function of time and repeat every 100 seconds, every 200 seconds, and then measure what is the concentration to do this accurately. So, now I already mentioned to you that the rate constant is a constant, but only when we work at the same temperature. If the temperature is increasing, the rate constant is also increasing. And there's a formula for that which is quite important. That's why I put it in blue. And the so-called Arrhenius equation. And this gives the temperature dependence of the rate constant as an exponential function, so a power of E. And there's a free exponential, A, which is not part of the exponential, which is a constant, the so-called Arrhenius constant, which is different for every reaction. And the factor E over minus EA over RT, well, the EA, that's nothing else than the activation energy. That's a certain energy that the reaction needs to be able to proceed. We will go into the detail of what that is needed. Again, this can be expressed in kilojoule, and it's smaller, so it's in kilojoule per mole of reagent. R is a gas constant. Now, in this case, we don't calculate with atmosphere, so it's a thermodynamic gas constant. So that means it's 8.3, 8.31, you know, I'm careless, 8.3 or 8.31, U per Kelvin per mole. The temperature always has also to be in Kelvin, not in Celsius. We can write this also in a logarithmic fashion. This is a natural logarithm, and the ground number of the natural logarithm is E. So that means that now the ln K is ln A minus activation energy divided by RT. Because, well, you know, if you take a logarithm, actually the exponents you can separate from the ground number as we do here. So if you look at that and we plot not K but ln K, the logarithm of the constants, the rate constants in function of 1 over the temperature, it's going to be a straight line. Because all the rest is constant. Activation energy is constant, R is the gas constant, and also A is a constant, the Arrhenius constant. So the slope is going to be the ratio between the activation energy and R. Now, this allows us to do some calculations, and it means if we know the activation energy, and we know the rate constant at a certain temperature, then we can calculate what is the rate constant at another temperature by applying this formula. And in this formula we know what is R, we know what is the activation energy, we know what are the two temperatures. For instance, we move from 20 degrees Celsius to 80 degrees Celsius. And we have one of the case, so the only unknown is K2. And now this can be calculated in that way. So if you have one rate constant, you have them all, as long as you have the activation and the temperatures. this drawing we see a kind of scheme. And now, normally we are used to graphs where we have the y-axis to the x-axis, and these are so-called scalar units, meaning one is proportional to the other. With the reaction coordinate, this is actually not exactly scalar. It's not in proportion. This is just two different states of the reaction, before, during, and after. That's the reaction coordinate. Before, that's the reactants. So, and we consider that the reactants are at a certain point in energy. Now we put it, in this case, relatively high. Doesn't have to be, we can put it relatively high. With energy, we could talk about free energy, but we could also talk about entropy and so on, depending on the case. Now, in order for the reaction to proceed, the molecules need a certain amount of energy. They can get this energy by the temperature, by the vibration of the molecules, by the fact that the molecules are moving around. They will actually collide with each other. And this gives the reagents in a more activated state, meaning higher in energy. And they need this state to be able to react with each other. So this activated complex is always higher up on the reaction coordinates, and the difference between the reactants and this activated complex, or it's also sometimes called transition state, is the activation energy. So you always go up. That means activation energy is always positive. Has to be positive. Now, afterwards, you form the products. And you see, it's all the way down from this activated complex. Now, if you now compare the reactants and the products, the way this is being drawn, it's an exothermic reaction, if we talk about entropy, or it's an exergonic reaction, if we talk about free energy. So it doesn't have to be. You can draw other reaction profiles. You could also start way down and then go up. Then this would be a non-spontaneous reaction, but just a different profile. But always the profile goes over a maximum of energy, because this energy is needed to break the bonds and to reshuffle the bonds to make the products. Without that, nothing is going to happen. Now, there's a couple of theoretical models that describe what is going on, and these models actually are not so much different from each other. So the first one is actually that well, particles are moving due to thermal movements. At some point they encounter each other and they collide. This collision gives the energy that is needed to break the bonds and to make the new bonds afterwards. So this means not all of the particles might have the right energy. Maybe they're too slow, maybe they don't have enough kinetic energy, and maybe they even don't have the right orientation with which they are moving towards each other. So this is only going to be a fraction of the collisions that are going to be efficient. And this is a kind of graph that explains, or at least tries to explain, how much actually of the particles have sufficient energy to do that. this is another graph, which is now, it is scalar. Here we have the number of molecules. This is their kinetic energy. So it means it's a distribution curve. And you can see, for instance, this is the highest number of molecules at a certain temperature, T1. So most of the molecules have an energy that is around here. Some of them have higher energy, but not so much. Yeah. Now we increase the temperature. That's the red line. T2 is higher than T1. You see the number of molecules that have higher energy, kinetic energy, they're moving faster, become higher. In fact, the curve is moving up towards higher energy. And now, we actually can plot on this curve activation energy. So suppose we have this first reaction with activation energy 1. So that means everything that is on this side, these particles have higher energy. Enough energy for the reaction to proceed. So now, if you look at the difference between the orange and the red curve, the orange curve was lower temperature, and you see there's much less of a cutoff than here. Here we have much more particles. So what can you derive from this Maxwell distribution, as it is called? At higher temperatures, there will be more particles that are ready to do the reaction. So in other words, at higher temperatures, K is going to go up. Now, if we go on with the collision theory, we can say there's actually a rate which is proportional to 3 factors. The first factor is R. In this case, R is not the gas constant, ideal gas constant, but is a so-called collision frequency. So what is the chance that the two particles will meet? And actually, this is proportional to the concentrations of the reagents that are involved. If the reagents are very diluted, the reaction is not going to go very fast, because it takes some time before the particles find each other. If it's going to be very concentrated, no problem. So you can see it's proportional, and actually proportional to the particles that are important in the slowest step of the overall process. So there might be 2 concentrations if there's a second order reaction, but it might also be only 1 concentration. Then there's a second factor, F, which is the so-called energetic factor. And actually, you recognize this term because it's the same E term that you also had in the Arrhenius law. So this is actually the fraction of the collisions that have enough kinetic energy. So we divide the activation energy by RT, and so we get the ratio. So actually this part here from this graph, that's the E over minus EA over RT. Then there's a third factor. This factor, just as the energetic factor, is something that is between 0 and 1. Of course, we would like to have it as close to 1 as possible, because that means high rate. So steric factor means, okay, the particles have enough energy, but they're not exactly under the right angle. You can say it's like playing with billiards. If you don't approach the two billiards at just the exact way, this is not going to be productive. So in some cases, this might be close to zero. In other cases, any collision will give the right product. So it depends on some steric factors. So, indeed, the F is proportional to these green or light green cutoffs. So, the second theory is the theory of the transition states. I already introduced this concept in the reaction profile. We had this activated complex. It's actually the transition state. So in this theory, you could say that it's as if there is an equilibrium, and we'll talk about equilibria in the next chapter, but it means the reaction is going back and forth between the products and the transition state, and between the transition state and the reagents. So, and an equilibrium, this will be explained much better the next time, is also having an equilibrium constant, large K. Now, this double cross here is just a notation to indicate that we are talking about the transition state. So, and now we can, let's say, write equilibrium constant, and typically the equilibrium constant is the ratio of the concentrations of the products over the concentration of the reagents. Sometimes the exponent is there according to the coefficient of the reaction. So it means we divide transition state concentration by reagents. Now, all of these formulas we will explain later on in the next chapter, but we can show that the speed or the rate of the reaction will be proportional to the concentration of the transition state. If the transition state is easy to reach, the reaction goes faster. And this is, of course, proportional to the equilibrium constant, because we just saw that. It's directly proportional. So that actually means that also, of course, the rate can be written as usual, as a first order, starting from the transition states. And so now we have small k for the rate constant, and we have the concentration of the reagents. It could be 1 when it's first order, or maybe more than one concentration term when it's second order, or something like that. That means, in fact, we see that k capital of the transition state is actually also proportional to small k, the rate constant. And this formula here, we will see later, that this describes any complexation constant. So it's related to the free energy. Now, of course, this we are actually recognizing, because energy divided by RT, and delta G of the transition state is the energy of the transition state. And of course, going from the reagents, we are talking about the activation energy. Now we can split the delta G in enthalpy term and entropy term. Delta H minus T delta S. Remember last chapter. If you do that, we we split the exponents into two exponents. And you can see this one is independent of the temperature. This part is dependent on the temperature. And in fact, the enthalpy of the transition state is nothing else than the activation energy. So you can see this is actually nothing else than the Arrhenius law. Because this now becomes the Arrhenius term A. Because that's a constant. The R is a constant, the delta S is a constant. So it's a kind of way to derive the Arrhenius law. So if we write the reaction profile, the transition state delta G is always higher than any of the products or reactants. This is always a positive number, so you have to go over a maximum. We can look at reagents and products, and actually we can do our reaction in two different directions. Normal directions, of course, we go from the reagents to the products. But you can turn your reaction around, especially if you have equilibrium. Maybe your products will form reagents. On the reaction profile, it's possible, you just go instead from the left to the right, you go from the right to the left. Now, I think what I have drawn here is, in the viewpoint of free energy, an exergonic reaction. The reaction products are lower in energy. That means delta G standards of the reaction, that's the arrow that is going down, is a negative number, and that also means this is actually a spontaneous reaction. Yeah. So, suppose we go in the other way, and we start with the products and we end up with the reagents. Now, we will turn around the number also of the energy, the free energy change. Because now the free energy change will be minus delta G. The arrow will go up, and because we are higher in energy when we reach the reagent. So you could also say that, well, we can look from the viewpoint of the free energy of the transition states, and you could just say that, okay, the free energy of or the free energy difference, I should say, free energy difference of the transition state of the reaction going up, and that's the arrow that goes from the left to the right, is, and that's the one here, is the free energy change for the transition state for the opposite reaction minus the energy that we have as a gap of the reaction. And that's what you see over there. We can write the same for the enthalpy, as you can see here. So the activation energies, in other words, so if you go to from the reaction products to the reagents, it means the activation energy is higher. You can see that we have to go over a much larger mountain. It also means the reaction will be slower. Yes. So this reaction is slower than the one that goes in the opposite direction, in the one from reagents to products. In this case. So, and we can also write the same about the entropy factor. Okay. the next time. So I'm going to stop a little bit early today. I hope you don't mind. And that way we can clear the audience before the next group is coming. Probably my colleagues will be happy. Okay, see you tomorrow, I think. Yeah.
As I can see,
Not that early as the previous days. If there are still any questions, I will remain here for some minutes.